Welcome back. We are discussing water quality parameters. In this video, we'll be talking about some of the chemical parameters. The first one is pH. pH gives an indication of acidity or alkaline nature in the water. Less than 7, it is acidic, and greater than 7 is alkaline. So number of methods are there, strip method and electrode method, whereas the limits for drinking water are usually 6.5 to 8.5. pH is defined as minus log H plus, the hydrogen ion concentration. It can also be written as log of 1 by H plus. So you can see here the pH value is detected using number of strips. The strip is taken and then dipped in that water. The change of color is compared with these colors here. Accordingly, the pH is noted. Otherwise, we are having electrode method. Usually, we are having an electrode. We are taking a water in a sample beaker. We are dipping the electrode, and then we are testing. Then display directly comes in the display readout. Before that, we used to have calibration of the instrument with a known pH of 4, 9, or 11. Separate tablets are there to have a calibration. Once the instrument is calibrated, directly it give you the indication, that display meter. Nowadays, for portable use, you have portable pH meters are also there. It will also give you direct indication. And here, this is the cap. This is the electrode inside. And then once you remove the cap, the electrodes are visible now. You just dip the electrode in the glass beaker. The information about the pH value is directly displayed here. So now we'll take up a small calculation. Two solutions, two water samples rather, having pH of 7.2 and 8.4 are mixed. They have 500 ml and 500 ml volume. So what is the combined pH? So now we go with the definition. pHA is equal to 7.2, which is nothing but minus log HA plus. This is 10 base common logarithms. So HA plus is equal to 10 to the power of minus 7.2. Similarly, HB plus is equal to 10 to the power of minus 8.4. Now, when you're combining these two, the total volume is 500 ml plus 500 ml is 1000 ml. So concentration of each is with respect to that particular volume of the sample. So concentration of each solution is 500 10 to the power of minus 7.2. So 500 to the power of minus 8.4. So H plus of the mixer is what the volume of this sample divided with total volume into here HA plus. Similarly, 500 by 1000 volume of the second sample by total volume into HB plus. So you are calculating and then getting H plus. Once you put back into this equation pH minus log HA plus, you are going to calculate pH is equal to 7.477. So actually, mathematically, if you see 7.2 and 4.4, 8.4, so it will be 15.6, so 7.8. So arithmetic average is 7.8, but the average pH or combined pH is not that value. It is changing with respect to logarithmic additions. Now, when you're talking about the chemical parameter, we should talk about the combining weight calculation. How you are going to calculate the combining weight? For example, you want to find out the combining weight of calcium ion Ca plus 2. If the molecular weight is 40 grams per mole, the number of ions here, the calcium plus 2 is 2. The combining weight is equal to 40 by 2, 20 milligram per 20 milliequivalents. Similarly, molecular weight of calcium carbonate, if you want to calculate, it is equal to 40 for calcium, 12 for carbon, and O3 is 16 into 3, 48, total 100 grams. And when you break up this Ca plus 2 or CO3 minus 2, so the number of ions in the reaction is now 2. So combining weight is equal to 100 by 2, 50 milligram per milliequivalent. So concentration of Ca plus 2 in terms of CaCO3, if I want to measure, this is usually happens in uh, the water quality parameters. They're often uh, expressed in terms of calcium carbonate. So concentration of Ca plus 2 in milligram per liter into combining weight of calcium carbonate divided by combining weight of Ca plus 2. For example, if Ca plus 2 is 60 milligram per liter, then applying this equation, 60 multiplied by combining weight of CaCO3 50, combining weight of Ca plus 2 is 20. So this is equals to 150 milligram per liter as CaCO3. Similarly, if you want to find out the combining weight of bicarbonate, how you are going to find out is here the molecular weight is 1 plus 12 plus 48, 61 grams, and the number of ions here is only 1. So combining weight is 61 by 1, 61 milligram per milliequivalent. If you want to find out HCO3 minus in terms of USCO3, if the concentration of bicarbonate is 61 milligram per liter, we are going to use the same equation, 61 milligram per liter of bicarbonate into 50 units of combining weight of CaCO3, 61 units of combining weight for bicarbonate, and which is equals to 50 milligram per liter as CaCO3. This information is helpful to find out or calculate the concentration of total hardness or total alkalinity. So total alkalinity is defined as the capacity to neutralize the acids or to accept protons. So it is imported in water due to hydroxide, carbonate, and bicarbonate components of natural treated water. So the alkalinity is defined in terms of hydroxide alkalinity, carbonate alkalinity, or bicarbonate alkalinity. Together, all the components together, if you are adding up, it is called as a total alkalinity. But the thing is, at any time, only two of the above three types of alkalinity are present. And this is based on the pH of the water sample. At pH greater than 10, hydroxide alkalinity is present. At pH between 8 to 10, half of carbonate is present. At pH less than 8, half of the remaining carbonate and bicarbonate are present. Usually the water samples are having a pH in the range of 7 to 8. So in such a case, what you are seeing is here either carbonate or bicarbonate are going to be present. How you are going to find out in the lab? So since it is neutralizing the acids, the water sample is titrated with a concentrated sulfuric acid. Here we are going to add two indicators, phenolphthalein and methyl orange. Phenolphthalein gives pink color only in the presence of hydroxide or carbonate alkalinity. At higher pH levels, the phenolphthalein will give indication of whether hydroxide or carbonate alkalinity is present. So up to a pH of 8.3, the change is from pink to colorless. And methyl orange is used for indication of pH below 8.3 up to 4.4. So the color is yellow or red. The change in color is indication of this reaction. The limits in drinking water 200 milligram per liter as CaCO3. So this is where we are going to make use of expressing the concentration in terms of milligrams per liter. So one more thing you understand is the concentration of these water quality parameters are mainly expressed in terms of milligrams per liter, mass per volume. So how much quantity of salt is present per 1 liter of sample. So total alkalinity, if you look at the simple calculation, how to calculate, so it is widely noticed that only carbonate and bicarbonate, they will be the contributors to the total alkalinity. So we are going to use the same formula what we had taken earlier. Concentration of bicarbonate in milligram per liter multiplied by combining weight of CaCO3, combining weight of bicarbonate, and concentration of CO3 minus 2 in milligram per liter into combining weight of CaCO3 per combining weight of carbonate. So this formula will give you the total alkalinity expressed as CaCO3. So bicarbonate, we are taking 61 milligram per liter, carbonate is 90 milligrams per liter. When we are doing the total alkalinity test in the laboratory, we can find out from the titration how much is the actual concentration of bicarbonate, how much is the concentration of carbonate by taking the experimental values. So now using this information, the combining weight of carbonate is nothing but the molecular weight of carbonate and the number of ions 2. And what you are going to get? You are going to get 30 milligram per milliequivalent. Similarly, combining weight of bicarbonate is molecular weight divided by number of ions 1, 61 milligram per milliequivalent. Substituting in the above formula, total alkalinity is equal to 61 into 50 by 61 plus 90 into 50 by 30, 200 milligram per liter as CaCO3. In a similar model, we can also calculate the contribution in the total hardness. The total hardness is caused due to carbonates, bicarbonates, chlorides, and sulfates of calcium and magnesium in water. So here, this is two types, temporary hardness as well as permanent hardness. Temporary hardness is caused due to carbonates and bicarbonates of calcium and magnesium. Permanent hardness is caused due to sulfates and chlorides of calcium and magnesium. Temporary hardness can be removed by boiling. Because having only carbonates and bicarbonates, after boiling, their carbonates are converted to carbon dioxide. So the total hardness is considered as a soft water if less than 50 milligram per liter and more than 200 milligram per liter calling as hard water. What is the importance of total hardness? Because of these salts present here, they causes a poor lathering of the soup, and in the boiler when you're using for heating purposes, these salts get deposited on the inner walls of the boiler or any container what we are using even for domestic purposes. It's called scaling. And because of the scaling, the poor heat conduction is possible. And how you detect in the lab? We detect it using titration with the EDTA. So EDTA means ethylene diamine tetraesteric acid. So this forms into a complex with Ca and magnesium, calcium and magnesium. That is the end point. The limits in drinking water is 200 milligram per liter as CaCO3. This is what is to be remembered here, CaCO3. In a similar manner, we can calculate the total hardness concentration if we consider calcium and magnesium are the major contributing ions. So concentration of Ca plus 2 in milligram per liter, and you multiply with the combining weight of calcium carbonate divided by combining weight of Ca plus 2 plus concentration of magnesium in milligram per liter into combining weight of CaCO3 divided by combining weight of magnesium. For example, calcium is 120 milligram per liter, magnesium 60 milligram per liter. In the laboratory, we can find out the concentration of calcium and magnesium separately from the total hardness. The calcium is can be easily identified by titration with EDTA. And once we know the total hardness and calcium hardness, we can easily calculate the magnesium hardness. Combining weight of Ca plus 2 is equal to molecular weight is 40 and number of ions is 20 milligram per milliequivalent. Combining weight of magnesium is for 24 molecular weight, and number of ions in the Mg plus 2 is 12 milligram per milliequivalent. So combining weight of calcium carbonate is equal to molecular weight of calcium carbonate divided by number of ions Ca plus 2, CO3 minus 2. So divided by 2, 50 milligram per milliequivalent. To apply in this formula 120 into 50 by 20 plus 60 into 50 by 12, you are going to get 550 milligram per liter as CaCO3. So now if you look at the total ions, the alkalinity or hardness, the bicarbonates are common. The hardness, along with the bicarbonates and carbonates, chlorides and sulfates are there. So they are mainly considered as a non-carbonate hardness. So in the alkalinity, carbonate and bicarbonate are also there. In the hardness, temporary hardness, we are having bicarbonate and carbonates. So how to have a relation here? If we want to find out the carbonate hardness, so we take a minimum of total alkalinity and total hardness. And non-carbonate hardness, it can be easily obtained by removing the total alkalinity from total hardness. For example, total hardness is equal to 550 milligram per liter. Total alkalinity is 200 milligrams per liter. The minimum of these two is 200, that is your carbonate hardness. That is contributing towards carbonates and bicarbonates. And non-carbonate hardness is 550 minus 200. This is 350 milligrams per liter. This is contributing mainly towards the chlorides and sulfates as part of the non-carbonates in the water. Then we are having one more parameter, important parameter, total dissolved salts, electrical conductivity. Total dissolved salts means we are having calcium, magnesium, and calcium, magnesium, bicarbonate, carbonate, sulfates, and chlorides in the hardness. Similarly, similar things are there even in the alkalinity. So now here in this, we are having some more ions, sodium and potassium. They are also possible in the water. And along with that, the anions, the regular anions, chloride, sulfate, bicarbonate, some other there. So few more are there which are not regularly used, available in the water. So these contributions are called as major ions. And few more ions such as iron, silica, fluoride, they are also be considered, but their contribution is very, very negligible towards TDS. This is called as minor ions. So in the major ions, sodium plus, sodium is coming from the cooking operation, sodium chloride, household salt. So this will come into the water as a salt. Sodium chloride, sodium sulfate, sodium carbonate, all are salts. Similarly, potassium chloride, potassium sulfate, potassium carbonate, all these salts. So other than calcium and magnesium, these two contributions are also to be considered here. When there are more number of ions, then ultimately it leads to passage of electrical passage of electrical conductivity through that particular water. More and more ions, more and more electrical conductivity is there. Now the contribution of all these ions is now is a part of the TDS. So what is the problem with this? This high TDS water, they cause salty taste to the water. Limits in drinking water is should be less than 500 milligram per liter. And then TDS, you can find out through gravimetric method, electrode method. Gravimetric method is nothing but you take a small amount of sample in a beaker and then you heat it at high temperature. All the water is evaporated, leaving only the salts. So you take the weight of the salts and divide it with the volume of the water. You are going to get the mass per volume TDS concentration. Electrode method, these are the different electrodes. This is a conventional electrode. This is a battery operated. So now you dip this electrode after calibration, then the display is directly coming into the readout device. Here, this is a battery device, the portable. So this is power operated. This is a battery operated, and people will take this type of pen type and instruments to the field to find out what the TDS, particularly when you're having household water treatment systems. And we usually measure the TDS using the TDS meters to find out that whether that treatment system at household is properly working or not. So relation between TDS and EC. So high amount of salts are present, high amount of EC is present. So they're internally correlated with each other.